Hello and welcome to this webinar on tense cable nets and grid shells for form finding with GSA. Now, why form finding? Architects say that form follows function, but we're engineers, we know that actually form follows force. Now, the majority of building structures, of course, this is quite limited. I mean, floors have to be horizontal, not much scope there for flexibility, as it were. And the main optimization that you do is just picking the lightest section size that will do the job. Other situations such as roofs and long span structures, there is more flexibility, and you've got the opportunity to make something sort of light, elegant and efficient, such as this is a fabric roof from the Edinburgh project down in Cornwall. Now, these lightweight structures, they resist loads not by inherent stiffness like the steel beams do, but by their form, their shape, their pre-stress and quite often large deflections. Now, okay, this wasn't the first fabric structure. I mean, we have had tents for thousands of years, but Fry Otto's roof to the Munich Olympics in 1972 was quite a major landmark in the whole architecture and engineering of lightweight tension structures. You can see quite an impressive structure. And you note that in those days, that was 40 odd years ago, that they had to use entirely physical models to do the analysis, because let's face it, computers were not in the position that they are today for that sort of analysis. Now, with compression structures, think columns just go up and down, not much scope there. Well, columns go up and down, they tend to induce bending moments and so on. So they don't have to go up and down. Sometimes non-vertical columns can be more efficient. I mean, here we have the crypt of the Colonia Güell church in Barcelona, excuse my Spanish pronunciation, by the architect and engineer Antonio Gaudi. He was a master of form finding and structural efficiency, and this was from end of the 19th century, I believe. Now, he tended to work using hanging chain models for optimizing the geometry, because obviously, again, he didn't have computers for that. Now you see on the left sort of a sketch from this Sagrada Familia church, and whilst we don't have the hanging chain model for that, it was destroyed during the Spanish Civil War, we do have images still of the Colonia Güell church, so you can get an idea of how he used these models to actually achieve the end results. Of course, today he would use GSA, but you can see from this photograph of the modern day Sagrada Familia, quite elegant and very organic structure, highly efficient. And you compare a cathedral like this to, say, the Gothic cathedrals, where everything's vertical and you need the flying buttresses to keep things stable. Yeah, it makes quite a difference. Now, this is a more modern example. This is from the Filling in the Future Expo 92 in Seville, an Arab Peter Rice job. These are ungrouted stone masonry units held together purely by the tension from those rods. Now, obviously, the ungrouted masonry is compression only, no tension capacity available, and you can use non-linear analysis to analyze these structures. We'll call that like a flip-flat model, using just sort of small compression-only elements, or between, and tension-only elements to model the rods. Now, again, if you get the geometry right, these compression-only structures can be amazingly elegant. And here's an example from 1939, Robert Meilert and his concrete shell for the cement hall in the National Exhibition in Zurich. Scale, well, you can see that there's a man on the bridge, so I'm not sure the exact dimensions, but it looked to be about 20 meters high, and thickness must be about 50 to 100 millimeters. I'm not sure, not a lot. Now, form finding. What do you get from the results from form finding? Well, one of the results is you have to get the geometry. Now, lightweight structures, the geometry is crucial with these. So the surfaces have to be double curved for stiffness, and there are three basic shapes: the conic, the barrel vault, and the high part. Likewise, in compression only structures like this, if you want to achieve that slenderness and so on, then the form is crucial to prevent buckling and moments and so on. And you can use form finding to create balanced structures such as this, where you've got the compression only and tension only elements all together. Another important output from the form finding is the exact fabric geometry. Now note in this photograph of the Marseillaise sculpture in the Tate Modern, fabric is fabricated, as it were, from strips which are then cut to shape and then bound together. If you get the shape of these strips right, we call the cutting patterns, then the end result will be the right shape. Another aspect you need to get right is the pre-stress. The pre-stress, again, is crucial to the end result of the structure and the final form. Form finding needs to produce balanced pre-stress forces to prevent wrinkling and so on. I mean, you can see, okay, this photograph of this fabric roof is under construction, but you can see at this precise moment that the pre-stress is unbalanced, and so you're getting ripples or high tension fields. What's it, wagon tension fields in the fabric? Similarly here, I mean, you can see during construction, pre-stress is not in position yet, and fully pre-stressed, and you can see all the wrinkles go away. And if you get the pre-stress right, you'll get a lovely smooth surface on your fabric structure. Similarly, in cable net structures, I mean, this is the Kuala Tensile Bridge in Brisbane. Form finding was used in this to generate the exact lengths of the cables prior to loading, such that when the bridge was constructed, the two parts would then meet up exactly in the middle. It was over a busy waterway, and there was no chance for sort of adjustment really as they went along. They had to get it right first time, which I understand they did. So, how does GSA do form finding? Now, we use a method called dynamic relaxation, and dynamic relaxation runs in a solver within GSA called GS Relax. So you sometimes hear this referred to. Older users will remember it used to be called Fablon, and it was a standalone program. Now, so it uses a method called dynamic relaxation, and it specialises in doing sort of general non-linear analysis, but also non-linear member buckling and form finding. Now, this non-linear analysis can be geometric and can be material, and it's called dynamic relaxation because eventually it is a dynamic method. It's not a matrix method. It uses sort of motion within the structure to try and find the equilibrium. Now, when the structural elements are moving around trying to find the equilibrium position, you have these unbalanced positions. So imagine there is the forces in those elements which are inducing acceleration on those parts, and what we're looking for is the balance position. Now, the balance position, there's no resultant forces on anything, everything is in balance, and we know that that is then the converged points. Now, because this is a dynamic method, things are moving around, and to make the analysis converge, you have to include damping as well. Now there are a couple of damping methods. There's a viscous damping, which is the default, but there's also a kinematic damping, which sort of looks for these, tries to look for the equilibrium positions and sort of jumps to those. And what it can do, well, because it uses the dynamic relaxations, it can deal with both simple non-linear problems such as cables and tension. You put load on it, the geometry changes until the geometry is such that it can resist the load. It can also deal with mechanisms such as the lower the pinned cantilever, and if you run this model in GSA, you will end up with it hanging straight down. So, quick summary of that. The GSA non-linear analysis automatically considers all your geometric non-linear effects. There's no limit on the type of structures used. Note, as we'll find out earlier, there is a limit at the moment on some of the elements you can use. You can't use all 2D elements, but it does model non-linear behaviour, both material and non-geometric, but also buckling as well. So form finding in particular. So form finding, is a method to find the new shape of the structure, the ideal shape, which is governed by the loads applied, but also the pre-stresses and constraints and so on. And it's different to most analysis methods because it doesn't produce forces and reactions as the end results. It produces a change to the model itself plus pre-stress forces. This new geometry and the pre-stress forces you then take on to further analysis for the static cases. Now once you define these forms, GSA actually includes 3 different methods to help achieve that. There's a soap film, there's a force density, and normal properties, and each of these has their own particular advantages in particular cases, and we'll go into those in more detail in a moment. Important thing to note as well, the boundary conditions of the model. Obviously on the static analysis you've got to have your support points. With form finding models you've also got to consider the edges of the structure, particularly, well, if it's a fabric structure you've got to consider the edges, and you can't have a fabric with just finishing myself. You have to have an edge to the fabric, whether the edge is a cable such as on the right, which is flexible, or a solid element such as the one on the left. Now also you can model cables within the fabrics, and you see example on the right there is a cable within the fabric, and you can do that if you wish. So soap film form finding, first of all. The name gives you a clue. Soap film is a mathematical model of a soap film, and a soap film basically wants to achieve its minimum surface area, or minimum surface energy, sometimes referred to as, and soap films have no stiffness in their own right, and we model these by having a sort of a soap film model for 2D elements, and there's an elastic band type model for the 1D elements. Now these elements all have no stiffness at all during the form finding, but they experience constant stress. Now because they have no stiffness, the nodes are actually free to move around, and therefore the nodes need to be controlled during the form finding. Otherwise you can end up with a mess like the structure on the right, or even worse. Now we have to use a thing called spacers. Now spacers are special chain elements which are there to actually keep the nodes spaced out, and they try to make things at equal spacings and so on. But the thing about space elements is that you can see the top part, there are a number of spacer elements, all with the same property, and they go together to form one spacer as a whole. And so the spacer is a sort of a super element, and it knows all the nodes along its length and tries to keep those equally spaced. Now, this is acceptable spacer. Unacceptable spacers are ones where you've got breaks in the elements, so you can't, such as the one at the bottom here, you can't have these two spacers with the same property. They have to have different property numbers. Similarly, you can't have any forks, but bifurcations in the spacers. They also all have to be going in the same direction. Spacers can be a little bit fiddly to set up to begin with. The end result is worth it, because the soap film method is very powerful if involved. Now, quick example here. Here is forming a high power shape. Now, GSA is the largest displacement non-linear analysis, so when we're doing a form finding, we just need to specify the constraint points, the end of 4 corners in this particular location. Everything else follows through. It is possible to move the structure too much, but if you do find that happens during form finding, just move the constraints some way, run the form finding, and then run it again. Now, that was a cable edge. This is a mixed structure, so we've got to form a saddle, so we've got 2 rings which are the fixed edges, and note during the form finding they're fully pinned, and the other low edges are cable edges, therefore they are free. You can include pre-stresses or forces in the form finding. I mean, if you're doing like an ETFE foil but cushions, you include a load within the form finding to then find the pre-stress shapes. Now, say I mentioned ETF cladding. Here's an example one: Beijing water cube from the last Olympics. Way this was worked, a form found and analysed was whilst the bubbles were actually sort of 3 layers of ETFE foil under inflation loads, each skin was actually analysed separately. Now, they needed a form finding to begin with because the large bubbles, the ETFE would yield under the inflation load, and so they had to be form found and then with the cutting patterns applied to get the right shape. Then, once it's under load, you then use static non-linear analysis to check them for inflation and wind loadings. End result: over 8 major international awards, and so on. And by the way, you can also use this inflation method for forming domes and grid shells. Just in passing. You also have a form called the conic. The thing to remember about conics is the radial pre-stress usually has to be higher than the circumferential pre-stress. Otherwise, during the form finding, they'll neck in the middle. The form finding will collapse. Now, also, you have to have a ring at the top. You can't have a conic going up to a point. It just doesn't work. But end results. Okay, this is a more unusual example of a conic structure because it's at the Museum of Modern Art in New York, some exhibition from a couple of years ago, using mylar. But the principles are all there: the mylar fabric, the cable edging, the double curvature surfaces, and in this particular case, what appears to be a small toddler holding the structure down. So let's look at how you actually do the form finding with the soap film model. Now, I've got GSA open already, and let me start a new model. Now, because I'm using soap film, soap film needs to have these spacer elements. Now, I'm going to create sort of a rectangular type structure, so I'm going to use the wizard, which will create the spaces for me. Note, if you're when you're creating your own structure and it sort of deviates away from that sort of shape, the wizard can be very useful for reminding you of the general settings. Now I'm going to add a material in here first. I'm going to add in a fabric material, and note the warp and weft stresses is an orthotropic material. I'm going to take the defaults, but for your real structures you need to speak with your manufacturer as to what the appropriate properties are for this. And I'm going to use the wizard to create a 2D element grid, and let's make it 5 meters square, and I'm going to break it up into half meter squares. Fabric property, I'm going to set these to fabric. Global axis, use my material just created, and note that fabric elements have no thickness, which means they have no self-weight. And so I'm just going to add in a kilogram per square meter for the self-weight of the fabric itself. Because it's form finding, I'm going to include spaces, and we note we have the internal spaces. Now, internal spaces are geodesic types, which means they will ensure that the nodes remain on the surface of the fabric. We do have the other types as well, and there are a number of choices on the spacer leg type. I'm going for ratio, and the ratio is 1, so they'll try and keep them ratio of 1 to 1 across the length of the spaces, and therefore equally spaced as much as possible. There are the other options you can play with. Similarly, edge spaces slightly different because these are bar spaces, so these are free to move in space and much more suitable for sort of cables which we have around the edge. So the edge elements can be a solid, a beam, can be a bar, can be a tie. I'm going to do a tie. Note as well, we often refer to cable edges on the fabrics. Cables themselves are, in GSA at least, a special element which we're not really going to cover today. They're similar to spaces, but whenever I say cable, think tie. So on this edge cable, I'm going to use just a circular 5mm diameter steel for a wire. Okay, and let's create that structure. And here we can see that we've got our basic structure. It's square. We have nodes at corners. We have spaces all everywhere, and you notice we've also got constant elements highlighted around the edge. This is fine because we've got spaces along the edge and we've got the tie elements along the edge as well. So if I just say the 2D elements, change that to elements. So we have 2D elements, the edge cables, and the spaces PG1 to PG start. Let's just colour those by property, and you can see each of those tell by the colour, so we have different properties for each of those. Now I'm going to do something a little more interesting. Now I'm going to add in some more properties. Now I'm going to add in another cable, so I'm going to say a backstay, which is going to be the same section size, and I'm going to add in a post, which is going to be a catalogue section, which is going to be hollow, and let's say something elegant, say a 60mm diameter. Obviously this nice, we need to check that steel design, but that'd be a good start. So let us take this structure, and what I'm going to do is I'm going to take those two corners and I'm going to modify those and pin those positions. These are going to be fixed to the ground. These 2 points here, I'm going to actually before I do that, let me add in the backstays property 2, which is going to be a tie. And so those 2 points there are also going to be pinned. And then I pick those 2 nodes there and I'm going to pull those up. I'm going to move them up by a couple of meters. And these are going to be my post locations. So I'm going to use the sculpt tool to extrude them back down. Clean beam elements. So those 2 nodes at the bottom are also going to be pinned, and those 2 elements are going to be turned into bars. Yes. Color by type. So we have our basic form ready to go for the form finding. Now, next stage is to define pre-stresses, and the pre-stresses are formed in the form finding. So soap film 1D. Now, these 1D properties that will match up with the 1D section tables here. So the edge pre-stress, I'm going to say 10 kilonewtons in those cables. The target backstay pre-stress, twice that. And the posts, I'm not going to ask for any pre-stress in those. Likewise, the fabric pre-stress, I'm just going to ask for a constant 1 kilonewton each direction on those. Now, the other thing I've forgotten, of course, is that if I was to form find this, these posts would fall over. So I'm going to add in now an artificial restraint on those. I'm just going to say restrain them in the Z direction, so they will remain at a constant height even though they're free to move horizontally. Right, I think I've remembered everything. Let's run this. So let's create a new analysis task, which is form finding using soap film methods. I'm going to add in a dummy load case, and I'm going to show progress and analyze that, and they say yes, I do want to modify the structure, and there it's run, and it says, do you want to modify the node coordinates? Of course. And I want to save those forces and so on as pre-stresses in the new structure. I say yes. And here we have the end result, which looks good. Now, I like that. But if we look on the edge, we can see it's reasonably low, but you also notice because it's balanced between the two sides, but you also notice these posts have moved over a bit. So what I want to do now is adjust this form finding so it comes up higher. So let's look at the direction of those elements. So the moment the warp is going diagonally across on these 2D elements, don't want that. Let's change that. Select property area 1, and I'm going to modify those to an angle of -45 degrees. So you see now the warp is going straight between the two posts. I'm also going to delete out the pre-stresses. Now you note it did create pre-stress forces. Don't want those, so I'm going to delete out, use the manage data, so they're all cleared away. as well. And I am going to say that the soap film pre-stress is now going to be in the X direction twice. And I'm going to rerun that form finding, so let me just adjust the view so we can see, and rerun that. You can see the end result is post over it further and the fabric ups up a bit higher. I'm happy with that, so let's free up those top nodes. That one. And then we can do a static analysis on this. So, static analysis, let me go and add in face loads. And let's say permanent loads and variable loads. And some wind loads. So, self-weight, everything, which is going to be permanent loads. And let me say property area 1, which is, this is snow load, so it's going to be variable in the global direction. It is going to be projected, it's going to be uniform in Z direction minus 0.6, and likewise the wind load is going to be low if it goes 4. This is going to be the local non-projected, and you'll say a load of 1 on that. So let's have a look at, just check my loads. Pre-stress on the structure. Notice I've got pre-stress on the post as well. I'll remove those in a moment. Self-weight, snow load, notice that's all vertical. Wind load, notice that's all normal to the surface. Now let's just go back, because that pre-stress on those posts is not a real one as such. Let's just reduce the view down to those posts and use the sculpt to delete displayed loading. That pre-stress was caused by the adjustment of the top X and Y coordinates and keeping the Z the same. So we have these loads. I'm now going to do a new analysis task, which is a non-linear static. I'm going to add in internal near pre-stress loads, permanent loads and snow loads, and the second one, which is pre-stress, dead loads and wind loads. Let's analyze those. Again, that's also using the nonlinear solver. Let's now note the deflections on here is are magnified, so it's not quite that scary. But we can then see deflections under the wind load, deflections under the snow load, and you note the fabric structures, they are a lot larger than you will get for normal stiff structures. But if we change that deformation down to 1:1 actual stiff deflection, you can see it's not so bad. Likewise, in the contours we can also see warp and weft stress results, and I'm going to use the new center values only because to simplify this. The contours can get a little bit confusing in some respects because these quads are warped. GSA actually turns all these into triangles during the analysis and then recombines the results back again afterwards. Hence, this slight discontinuity in the contours. If we take the center results, then we can see the loads in a more simplified form. Right, let's moving swiftly on. Soap film summary. Got to include spacers. to control the structure. You've got to define the pre-stresses, so the cable pre-stresses. If they're cables, if they're solid, you just pin them in a location. And the 2D element pre-stresses, and note you can define different pre-stresses in the warp and weft direction for soap film. Next method, force density. Lot simpler, lot less intuitive. Now, soap film is very good for both fabrics and cable nets. Cable nets quite often found in with the force density methods. Now, force density, say, has no spaces, so in that respect it's much simpler. But during the form finding analysis, the stresses are set in proportional to the element dimensions. Specification forces. So, so this is length times force density, or area times force density. And for example, this initial bar arrangement first, with different force densities, the end result is different lengths of the various elements. It's very quick, quite organic, but it's slightly more iterative because it's not quite so obvious maybe what the end result will be. But you can use the cable nets, start initial form and end results. Okay, let's have a quick look at using force density for a cable net structure. So let's go back to GSA, close up all these other bits, and I'm going to create a new structure. And I'm not going to use the wizard this time. I'm just going to create blank start, and I am going to draw in a 10 meter long element. And I am going to split that up into 1 meter sections. And let's look on the elevation, and I'm going to select that one, and I am going to copy that up 2 meters to form the top bar. So this is going to be a bottom cable of the bridge, top cable of the bridge. I'm then going to add in some diagonal elements. So this is going to be a pure tension structure, and let me just copy those. I'm just going to reflect through the XY plane and just move those up. Okay, let's select all those, and I'm going to copy those over in the Y direction by 2 meters. That's good. And then I'm just going to add in some cables bottom. I'm going to use a volume to exclude the top parts. And again, I'm going to draw in some diagonals, making sure to select the nodes and not the midpoints of the elements. And again, reflect those through the X times the XZ, and move those 2 meters up. So I've got the structure in the form position. I'm going to select all those. I'm going to modify those. These are all tie elements, and I'm also going to create a number of shape properties. Now, section 1 circular, just 5mm diameter, and I'm going to create 4 sections. Bottom, main cable, top main cable. Can't spell today. side diagonals and base diagonals. So let's apply that. So everything's property 1 at the moment. Look from the side, select all those, and just colour by property so we can see what's going on. Modify those, property number 2. Select all those side ones. These are going to be property number 3. And look in plan. Select all those. Select property number 4. Excellent. Let's go back to the plan view, and I just need to pin the ends. And there is our basic structure ready for form finding. We now need to set up the form finding properties. Now this time it's force density 1D. And for these bottom ends, remember this, each line relates to the sections. Let me just copy those values. And I'm going to say the bottom cable, I'm going to force density of 40, quite high pre-stress. Top cable, quite less, maybe only 10. And the sides, a nominal amount. If I now run form finding using force density, again the dummy load case, and analyze that, you see it's now found. End result, so you can see it has form found. Quite nice, elegant structure, and I like that. And obviously we can then go ahead and apply static loads onto that. Now, mention about the prestress. Remember the force density, we were asking for 40 and 10 and 1. Let's say property beam 1. And let's look at the values of those. So these were all 1 meter apart to begin with. Some of these are stretched, and so we're getting a force density of a pre-stress of a little bit over 40 for these, because again it is proportional to the length. Top bars, top cables 10. I'm getting generally pre-stress of 10. Sides 1. Some of these elements are a couple meters long, and if we were to select, let's say, those 2 nodes, see you've got pre-stress of 2.105, and if we look at the selection of those 2 nodes, we can see they are 2.105 meters apart. Similarly on the base cables. Okay, so force density, quick summary of that. No spacers. Much easier than soap film in that respect. You need to define cable pre-stresses in terms of their force density, and similarly fabric pre-stress. You can use a fabric, but you only have a general force density. You don't have the 2-direction choices that you do with the soap film. Third method, norm properties. Now, norm properties doesn't use these special form binding properties, use the element stiffnesses themselves, and end result is large scale deflections on the structure, which is very good for compression only structures such as forming arches and domes, grid shells, Mannheim World Garden Exhibition, as you might recognise. Grid shells obviously tend to be much more organic than straightforward domes. So very lightweight timber structures. Again, the geometry is crucial to the stiffness of these structures to minimise bendings and so on. Danger loads on these, things like snow loads, obviously asymmetric loads. This is again from the 1970s, 1975. Hanging chain models were used to create the geometries, and then very careful measurements to get the geometry. Today we'd use GSA for using either soap film method, using inflation pressures, or these normal pressures. So very good for shell type structures, which you can't create using the soap film or force density. Can you also use it for like roof trusses and so on. So it's quite a flexible method for producing very efficient structures. So let us have a look at that in action. So again, I'm going to create a brand new blank model. I am going to add in a node just at 0, 0, 0, and I'm going to extrude that because I'm going to create for this shell. Now note, shell elements can't be used in form finding directly, so I'm going to use them indirectly. Basically, I'm going to cheat. I'm going to create a grillage with shells in there. So let's use this sculpt method to extrude it in the X direction. Let's say 20 increments at half meter spacings, and I'm going to include beam elements along there. So this extrude copies and creates elements as well. And now I'm going to copy, extrude those beam elements in the Y direction again, 20 increments, half meter spacings, include beam to grillage. I'm going to include quads as well for the end shell. And you can see there is our basic structure. Now, domes, quite often you fix at the corners, but I'm going to do something different. I'm just going to pick that's 4 midpoints of this structure, and I'm just going to pin those in position. Now we need sections on these. Sections is very important, so I'm going to, the beam elements, I'm just going to say concrete, and I'm just going to give them a nominal property. These beams are only there for form finding. So the property is reasonably arbitrary. What's more important is the shell properties at the end, which we're going to use static analysis on, and global again, and let's say 50 millimeters thick, and keep all the other properties normal. So it's going to be quite a thin shell on this. We need loads. Let's give be quick, dead and alive, old-fashioned names were like this. So grid loads, dead load, self weight, and I'm going to create beam loads for the imposed loads, and this is going to be the snow load. Oops, minus 0.3 half meter spacing grillage, and I'm going to create that load the same in the 2D elements. That should have been projected minus 0.6 because it's a pressure rather than the beam load. I appear to be doubling up the loads, but I've also doubled up the elements, and what I'm going to use then is staging in the analysis to only analyze or form find one part structure at a time. So analysis stages, I'm going to say form find stage, which is going to be property beam 1, and static load, which is going to be property area 1. So I'm going to use half the elements at a time, but because they share the nodes, when we form find the beams, the shells will follow suit. Now, speaking of loads, let's have a quick look at these. Oh, no, that one. So dead loads, live loads, that's good. And so the form finding on this, units task, form finding, and I'm going to analyze only the stage, which is going to beams only. Form find properties, add in, I'm going to take the dead and live loads, and I'm going to factor them by minus 1000. I'm going to take the static loads, reverse them, and point them upwards. don't magnify. Analyze that. And there we have the end result, and you can see it has form found up. I want to modify them to coordinates, but I'm not interested in pre-stress forces this time. And so we have a shell structure. Like that. I'm happy with that. If we want a bit more, I could just rerun the analysis, and that pushes the structure up further. And once we're happy with the geometry, we can then run a static analysis. Now, this is deliberately going to go wrong, but I'll show you. So, static analysis, I'm going to say, just create a default load case is dead and alive. And as you can see, it has told me that there's some 2D elements which are warped too far out of plane. If I just double click on these, you see it's basically selected all these 2D elements. These 2D elements, these are quads and these are warped. 2D elements need to be two-dimensional, they need to be planar. These are not. So having those selected, I am going to split those down into triangles so they're not warped. And then I'm just going to run analysis case 2, and so the end result, look at displacements for example. Displacements on the structure minuscule. In fact, let's do a combination case. 1.5 A3, and the stresses max and min forces on this. You see, it essentially is a compression only structure with a small amount of moment, due to the fact that the form finding wasn't exactly the same as the end result, because we have those edge beams which would have had a higher load on, and therefore you do get that slight discontinuity, slight adjustment in the deflections. But slightly more careful form finding, and you can get some end shells which will barely move at all. So normal property summary, no spaces, no form finding properties, just the structure elements themselves. Use those properties to achieve large and permanent deflections. So where next? If you're an Arab user, or you've already got GSA Fabric Suite, then just activate the form finding in your preferences and go ahead and have a go. If you're other GSA user, let us know. We can request a GSA trial. If you're not a GSA user at all at the moment, download GSA from the website, and that will have everything in apart from the form finding and fabric elements. Speak to us and we can organise a trial for you.